Okay. So what is a black body? A black body is it's a hot thing that's radiating hotness. Okay, so think of like red hot coals or white hot iron or something like that, or the sun. In what sense is it black? It's black in the sense that it absorbs the radiation that falls on it, and it doesn't reflect the light that falls on it. In other words, it doesn't scatter light, it just absorbs it and then emits the radiation at all levels according to its temperature. Physically speaking, that's an approximation, right? Like most black things are, you know, you've got a bit of a sheen on them. If you shine light on it, you might see some reflection. You've seen that like real fancy paint that Anish Kapoor has, where it's like that super nice matte black that's really close to black body. The classic black body is the black hole, but that's too weird, so forget about it. So it's a perfect absorber. So the light is described by there's like displacement Wien's W-I-E-N, displacement law, and there was the Stefan Boltzmann law, and there was Planck's law, and these were all laws that existed before statistical mechanics came along and explained what was going on. So you can think of that as the pre-Einstein. Pre-Einstein. You've got yourself your Wien's law, which is that the maximum of the frequency is increasing with temperature. So higher temperature moves the peak along. You got Stefan Boltzmann. You know Stefan Boltzmann? Have you seen that one? No? You did in first year? Fantastic. That's, yeah, that the rate of energy loss, dE dt, the power goes as t to the 4, where sigma is some constant. And you've got Planck's law. Planck's law, which is that this one actually explains the shape of the whole thing and has a funny H in there for the first time. And everyone was like, wait, what's that doing there? And then Einstein comes along and explains all of this very easily because he understood statistical mechanics and quantum mechanics. Okay, so this is where we're at. So we need to figure out what all these things are, and we need to make some approximations to understand it. So what is light? What are photons? In quantum mechanics, all particles are described by their quantum numbers. So what is a photon? Photon is a thing which is a boson, which is what we're talking about today, not last week. Has spin s equals 1. They're ideal, non-interacting. That's kind of, these are like the perfect little toys to play with. Yeah, if you want to study statistical mechanics. Linear dispersion, well, that's a bit different. Linear dispersion, because they're massless, they go at the speed of light, and the energy is not p squared over 2m because mass would be 0. Don't make any sense. It's PC. E squared equals p squared plus m squared. C is floating around somewhere, so E equals PC. And there are two polarizations. Why are there two polarizations? Because they're transverse waves. And this is all you need to know about photons. Okay. So these are the things that we know about photons. And now we're going to start going, okay, what are we going to do with these things in statistical mechanics? Yes. Yes. Nope. Nope. So the question was, gases bounce off each other and go in all directions. That's interactions. Photons don't interact, so they don't actually do that. But are they going in all directions? It depends. Maybe they're all like, when I'm thinking about photon gas, I'm thinking about them bouncing off the walls of the box, or I've got more like a black body inside, and the walls of the thing are at some temperature, and so it's creating and absorbing photons all the time. The thing about photons that makes them different from gas particles that you're thinking of is that you can create them or absorb them. Yeah, you can just create a photon, whereas you can't create an oxygen just like that, can you? You can't just be like hanging out and now all these oxygen just spitting out off the side of the box or just getting absorbed into the side of the box. Photons, you can. You make them for free. Yeah, all you need is a bit of energy. Bam, you got yourself a photon. Okay. You can imagine it as bouncing around in a box with mirrors, but I think a better way is to think about it as being an iron box at some temperature. If a photon hits the side of your box, then it gets absorbed by the iron. Yeah, but the iron also emits. Yeah, which way does it emit? Well, it's all got a rough texture on the outside, emits in all directions. Yeah, so you've got this gas inside. It's constantly, the photons being created and destroyed. Yeah, inside the box. Yeah, that's a black body. That's a black body. Okay. So we want to describe this thing. Does everyone understand the polarizations of the photon? You're all good with that? Yeah, wiggling up or wiggling across, or circular or whatever. Okay, cool. Third year, it's good. All right, so we need to describe the gas. Describe gas. Firstly, it's bosons, and it's quantum. And that means if I can create and destroy particles at will, then and I'm at some temperature, what's the distribution I should use? What's the name of the distribution I should use? I can create particles, I can kill particles, and I can create energy. What's it called? Grand canonical. Grand canonical quantum ideal gas. I get a real saving here. You guys seen this one before? So good, right? So good. There's another thing there that's not obvious. For photons, right? Now, previously for boson-Einstein condensates, we showed that for a boson, mu had to be negative, otherwise you had all kinds of problems. Now, for photons, mu equals 0. What? Why? There's a simple explanation for this, and then there's like a QED explanation for this, and different ways of thinking about it. But if you say, okay, so why? I'll say this, that the photon number is not fixed. You can create them and destroy them, right? That's the idea of the black body. You created and destroyed. If you take a Helmholtz potential, Helmholtz, F as a function of T, V, and N, then that should be maximized with respect to variation of N. And that will give us that df dn bar equals 0. But also df dn for that potential is the definition of mu itself. How do I then, if I look at these two things and I say, well, I'll maximize this thing with respect to n, but oh my God, hang on a second, this thing is also equal to mu. All right, mu equals 0. All right. Is that convincing? Medium. So mu equals 0. You can just take that. Another way of thinking about, of course, is that you just take it, set mu equal to 0 and see what you get. And if it corresponds to the physical world that you live in, you've gotten the right chemical potential. Yeah. Don't forget, this is physics, right? You have a set of assumptions, a set of axioms, you run through it. If it agrees with reality, then we're like, good theory, mate. Right? Okay. Yes, sir. It should be extremized. It should be a stationary point. Stationary point. Stationary point. It's E minus TS. So in fact, it should be minimized, but that's irrelevant. Stationary point. Where was I? Thank you. I'm lost. Density of states. Density of states. So density of states is what we always need. We've got dn for some particular. Well, this is always my least favorite thing. I've got two polarizations. I've got my favorite formula ever. Good. I should write that, what that is. Two polarizations. This, by the way, this is like a little bit of a technical lecture, this one. So mathematically technical. So if you don't remember every step of them as we go, it's okay. I don't like expect you to remember everything that we do. Right, 2v d3k over 2 pi cubed. All right. What's k? K is momentum. What's it called? Wave number? Wave number. Wave something. K's, I think it's wave number. Right, yeah. So, density of states. Next. All right. All directions are the same. Equal. Isotropic. So we don't care about directions. Then we're going to have d and k is equal to 2v 4 pi k squared dk over 2 pi cubed. Or we can write it in terms of frequency. Frequency, angular frequency omega, 2v 4 pi omega squared d omega. How is omega related to k, everybody? How relate omega to k? Really? Yes, speed of light. Thank you. Oh. Equals c cubed omega squared d omega. Okay, so these are all the things that we might need for our little puzzle today. And thermal equilibrium at temperature T, the number of photons with frequency omega to omega plus delta omega is dn, number that have frequency omega, is v over pi squared c cubed, omega squared d omega, that's what we have up there. But we have to put in this e this the statistical factor n. Okay, so that is the number of photons with frequency between omega and omega plus d omega, right? That's the number of particles. What's the energy? The energy of those photons right, in that frequency range, the energy of those is dE with frequency omega. It's the number of them times the energy h bar omega. Yeah? So I get V over pi squared c cubed h bar omega cubed d omega over e to the h bar omega over kt minus 1. This is Planck's law. We don't even have to do the integrals. All we have to do is look at how the maths works. So statistical mechanics has just given us Planck's law for freeze. Once you've worked out everything about canonical distributions, ideal gases, bosons, and so on and so forth. But now we've got Planck's law. Yeah? Looks good, right? Planck's law. Let's have a look at Planck's law in more detail. Right, the minimum. Oh, no, the maximum. Planck's law. Omega versus dE omega. D omega. So the fraction at omega. What does it look like? It looks like this. It goes. This part here is exponential. That's where that part dominates. This part down here is going as omega cubed. And there's some maximum value here. If you take the derivative of this thing, you'll find that the maximum is at h bar omega over kt is around 2.82. That's just from what we already have. Therefore, max. Therefore, omega max is proportional to the temperature. That's Wien's law. Nice, huh? Okay. A little side is that the sun's surface at 6,000 Kelvin has a wavelength peak of 850 nanometers. 850 nanometers. So just in the infrared for us, we can't see it where the peak is, but we're not too far off the peak. Okay, what's the total energy of the proton gas? Total energy of the photon gas is, take the total energy, it's going to be the integral from 0 to infinity of all of the energy that comes from each one of the frequencies. And you get V h bar pi squared c cubed integral 0 to infinity omega cubed d omega over e to the h bar omega over kt minus 1. This integral, right, I don't expect to be able to solve it, but I do expect to be able to transform it into a standard integral so that then you'll have v h bar over pi squared c cubed. I take out a factor of kt over h bar to the power of 4, and I will get standard integral that looks like this. X cubed e to the x minus 1. This is the integral that will be in the exam if I was to ask you a question about blackbody. I would give you that integral. I would be like, here is a standard integral that you need for this problem. I don't expect you to know how to do this. It ends up as pi to the power of 4 over 15. Can you be able to do that? Most of you would be able to do it, but if you don't know how to do it, then it doesn't matter. And I definitely wouldn't expect you to do it under exam conditions. Definitely expect me to be able to do it under exam conditions. But nonetheless, we've now worked out that the total energy is, where are we? V pi squared over 15 kt to the power of 4 over h bar c cubed. What's this one? Stefan Boltzmann. Great. It's close to Stefan Boltzmann. They actually need a DEDT, but that's okay. Let's see how we go. So that is the total energy of the photon gas. Okay. It's exactly the area under the diagram. Because that's the area under the diagram is the y-axis. The y-axis is dE d omega. If you integrate that, then you get the area under the, yeah? Yeah. So one, like, this is like the probability density function. This is like the cumulative function, right? So sum up all the little bits, you get the answer. Okay. Good. So that's Stefan Boltzmann. Okay, so we're getting close to it. This is actually going pretty well. So now we're going to get into the bit that really gets messy, which is what is the flux going in a particular direction? And that's called blackbody radiation. So here is where we go off-piste. This is the bit that confuses me, and I have to be really careful when I do it. So I'm going to do it, but this is the bit where, like, it gets funny and I start making mistakes. So I've got some blackbody. That guy here. There we go. Does that look nice and black? None more black. There we go. Sorry? Slightly reflective. Yes, it's got the wrong patina. It's round. Yeah. And there's light coming off of it in all directions. It's supposed to be like going out normally, but you know, that's life. Blackbody. And the question is, how much is going off in some direction? So if I look out, what is the radiation going in some direction? That's my N direction. And this is a solid angle here of d omega. And how far away is it? It's CDT, which is a nice workout there, right? So now what I want to know is blackbody radiation. Whoa! Gotta remember your things, isn't it? All right, let's go back to this one. All right, so blackbody radiation. This is where the integrals get nasty. Blackbody radiation. So blackbody radiation. Okay. So we've got photon gas, light's traveling in all directions. How much comes out in what direction? So what we want to know is we want to know the amount of light going in the direction n. So flux of energy. Yeah. Flux of energy through that is dE equals C dt, right? So in other words, it's like how much passes through every second. It'll be like, there's like a box here. And there's stuff that's inside that box. That's what's going to pass through in time dt. Yeah? So C dt, it's in the direction n. It has a rate, frequency. Whoa, okay, there's a lot of stuff. So what we're going to do is integrate over the frequencies and put a little omega there because it's just the ones with the omega. We're going to integrate over frequencies and average over d omega. So integrate over the omega, average over solid angles, and then we'll get the amount of light okay, so that's the plan. This is fine. Right, dEdt equals, going to integrate C dt squared C cubed omega cubed d omega over either h bar omega over kt minus 1 cos of the angle theta. We're going to define the angle theta in 1 second. Average over solid angle. Theta is the azimuthal angle, or the polar angle. Yeah, polar angle. So we're going to get to that. Equals h bar pi squared c squared integral. Now we're going to put in actual things. 0 to infinity of omega cubed d omega putting in my limits. I'm going to integrate over what's the one that goes that way? The non-polar. That's the azimuth. Okay. That's on azimuthal angle, polar angle. Come back to 0, pi and 2. This one usually goes up to pi, right? I'm going to put cos theta, sine theta, d theta over 4 pi. Okay. Are we good? Yes. So if I have a chunk of light, yeah, and it's over here, let's say, it's going out at some angle theta here, relative to my normal. Yep, that works. Some angle theta relative to my normal. You might think it's not going to hit. It's not going in the direction n. I don't need to worry about it. You would be wrong, because this light can be resolved into a component which is going in the direction n. Yeah. Component there and a component in this direction. I can break it up. Yeah. So the question becomes, right? If I average, and that's why I say average over d omega. So I integrate over that whole hemisphere, which have components going in the direction n. I average over that whole hemisphere that have some component going in the direction n. And then I take this cos theta into account, which then gives me the proportion of that, which can be projected into the direction n. This is the correct way to do this integral. Because that's just the hemisphere. So we're going to go from theta is 0, is the stuff that's going directly in that direction. The stuff that's going this direction is going to be 0 because it's going to be at pi on 2, this cos theta is going to give me 0. So that's no component going that direction. But the stuff that's going this way doesn't give me a negative amount of flux going through here. Yeah? No, understand, like that's, so this is naught to pi on 2. From pi on 2 to pi, that's the other half here. Yeah? This hemisphere does not give me a negative contribution. If I put it in there with a negative, with the cos theta, I get a negative. Oh no, we all like, so the usual way of doing these integrals, right, is that a double integral over d omega goes to integral from 0 to 2 pi d phi, integral from 0 to pi of sine theta d theta. Yeah, that's the normal one.
We're still going all the way, like imagine the pole is where I'm pointing. We're going from 0 to 2 pi, but then we're still doing the 0 to 2 pi all the way around. So you don't go from
this theta is like, it goes from 0 to pi. There is no from pi back to 2 pi again. This angle here goes around from 0 to 2 pi. Just think about, okay, it's like the Earth. You got your Earth, it's pointing up. What do you mean? It's the same thing, just this way. Rotated it. So this is why it's called polar angle. It's like relative to this. So theta goes here to here, and then around this way, it's 0 to 2 pi. Yes, it's rotated 90 degrees compared to how you normally draw it. Which is, in retrospect, unnecessarily confusing. Maybe that can be the theme of the whole course. Take this integral and do it. You get dE dt is equal to blah, 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 pi squared over 60. I love that. Pi squared on 60, kt to the power of 4 over h bar cubed c squared. That, my friends, is Stefan Boltzmann law. That's the Stefan Boltzmann law. Okay? So this thing, which is pi squared over 60, k Boltzmann constant to the power of 4 over h bar cubed c squared, that is in humanish units. That's the one that's 5.67, 10 to the minus 8 watts per meter squared per 4th power Kelvin. Right. Stefan Boltzmann constant. Okay. Yeah. That in a sense is the end of it. What I do talk about in the notes, which I might as well do for funsies, is talk about the thermodynamics again. So we cheated. And the cheat that we did was to start with the occupancy rather than the partition function. You can always go back to the partition function whenever you feel like it. So mu equals 0. We already worked that out. Energy E equals h bar omega. And so we have that the curly Z1 is equal to 1 over 1. Yeah, I'm going to check this one out if you want. Beta mu minus epsilon. That was the partition function for one particle of my ideal bosonic gas. And that gives me 1 over 1 minus, now mu equals 0. So this is now just e to the minus h bar omega over kt. Cool. That is my partition function. Like I said, we don't need it, but we can have it. So let's have it. That's the partition function. So that means that we can do things like log of the partition function is the integral of log 1 over e to the minus h bar omega over kt. Can integrate those over all of the frequencies, and you get to this nasty business equals minus the integral. And I'm just copying down because I can't be bothered working out exactly how this all works. So log 1 minus e to the minus h bar omega over kt. And then dn, which we worked out before, pi squared c cubed omega squared d omega. Okay, so that is the sum of, that's the partition function for all of them, equals minus, pi squared c cubed kt over h bar cubed integral of not to infinity of x squared log 1 minus e to the minus x dx. Now you can treat that as a standard integral, or I show you how to do it. It's just integration by parts. It's actually not too difficult at all. Gets back to something that we need very, very easily. And you'll find that that thing is equal to minus 1/3 pi to the power of 4 over 15. All right. I don't sit around doing integrals for funsies. I usually just plug them into Mathematica. Put all that together and we get that's the curly partition function. Sorry, that should have been the logarithm of that boy. The logarithm of the curly partition function is v pi to the 4 over 45 kt over h bar c cubed. Okay, so this is now we have an actual partition function, huh? How fun. Partition functions are good because then we can write down potentials like this one. And so like nice, just to remind ourselves that actually we can always go back to just our known statistical mechanics. And once we've got our partition function, we have everything. This minus kt log z, that's equal to, by definition, that's f minus mu n, mu equals 0. So I can just write that the Helmholtz and the Grand, they're the same in this case. Both of those are equal to minus 4 pi, no. Oh. You know what? Just write it out. Ugh. V pi, there's a point to this, I promise you. 45. Helmholtz potential, k to the 4, h bar cubed, c cubed, t to the power of 4. Doesn't look so bad. It's also minus 4. It's 4 sigma. It's sigma is Stefan Boltzmann. Okay, so here we go. We got a Helmholtz potential or Grand potential. In this case, they're the same thing because mu equals 0. So that's good. I can do things with it now, right? You can say entropy. Entropy S equals minus dF dt at constant V equals 16 over 3 sigma over C Bt to the power of 3. Entropy goes as temperature cubed. So nice. Pressure. Pressure is funny because you think, oh, how do I have to think about the pressure of a photon gas? Does it even have pressure? It must have pressure. What's the momentum of one of these little guys? I don't know. We need to know. I do not need to know. All I need to do is think about the gas itself. And I'll work out that the pressure is given by that. That looks good. If I work out that in terms of the total energy that I calculated earlier, which was sigma t to the power of 4, I get, which is great. Yeah, simple formulas. Okay, so this last part of this lecture was just to remind you that you can always go back to the partition function, Very simple for ideal gases. You can always go back to the partition function, work out your potential, work out your entropy, work out your pressure, all that stuff. Okay. It's almost mechanical. The hard part is getting to the partition function. Once you've gotten to that partition function, then you've just got some mechanical stuff to do, to play with. Yeah, so it's not too bad. So that is what I wanted to get up to today. I can't believe I've gotten through it early. I'm super proud of myself. I think I've done a great job. And along the way, I even drew a really pretty picture of a black body. So it's been a good day. Are there any questions that you'd like to ask? Yes. Such a great question. The question was, for those at home, when should we use F and when should we use E? Who's got the answer to that question? Yeah, close. The question was, is if there's no mu. It's actually slightly different to that. We have free variables and fixed variables. Now I'm going to have to go and try and find it, and I don't have all of my notes here. So thank you for that. I really, really appreciate it. When do I use F? Okay, I just got to find the right part of my notes. So E is a function of what usually? We write E. Yeah, so we write something like this: GE equals. Now, this is where I'm going to mess it up. TDS minus PDV, is that correct? I've got the signs right? Thank you. So here, we're thinking of energy as a function of S and V. Yeah? What about F? We usually write F as a function of what? E minus TS, yeah? So that gives us. That's right. Okay, let's do it. Let's do it the long way because I can't remember either. So, you know, oops. This is, by the way, this is a very unfair question because I have told you that I don't like thermal physics. So it's really unfair. Yes? So here we have one where F is a function of V and T. What's the advantage of this over, what is the advantage of this one over this one? When would I use this one instead of this one? I would use this one when I have temperature varying. So if I have a situation where I want to know pressure, pressure is equal to dF dV minus sign at constant temperature. Yeah? That's a nice definition of pressure. If I was to use energy, I can also get pressure. Yeah? Pressure here is equal to minus dE dV at constant S. Okay, it's the same equation. It's allowed. The problem is that setting up a system that has constant S may not be trivial. It is trivial in some cases. When is constant S easy? Adiabatic system. Yeah? Adiabatic system is the microcanonical distribution. Microcanonical, yeah? Microcanonical, I have adiabatic system, fixed entropy. In that case, this is a great way to get into the pressure. What about in the canonical distribution? In the canonical distribution, I have a heat bath. So the entropy is going all over the shop, but the temperature is fixed. This is a better equation. Both of them are good. Both of them are going to give me the right answer. Yeah? It's just a question of whether or not my S is fixed or my T is fixed. That determines whether, yeah. So you remember, like, this is all coming back down to Paul's stuff. Yeah. So all the different distributions and functions, Gibbs free energy, Helmholtz free energy, all that stuff. It's basically coming down to what do I need right now for my particular system? What's the easiest way to get to the thing that I want? Yeah. So in the canonical distribution, we have F. F is good because I'm thinking about temperature and volumes. If I'm thinking about the grand canonical, then I also have mu dn. Yeah? Okay. Yes. This one? Back. Still proud of this. It's great. Yeah, that's d omega. Yes, I can. So I take this thing and I want to get to a total energy per unit time. Yeah. So I take this thing, c dt, blah, 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 blah. And I'm taking this dt down here. Okay. That will give me the dt for a particular frequency. Okay. The dt. By the way, this thing looks funny, doesn't it now? It's got de omega on both sides. Yeah, it's total versus not total. So now it's confusing. Okay, it doesn't matter. I'll come back to that. So the EDT, I want to integrate over this omega cubed. That's the C. This C is this C. Yeah. This part here, that is my dE omega from before, from previous slide. And then I've got N and there's a volume's gone walkabout too, right? Volume's gone walkabout. So this is density as well. Oh no, that's where that was over here. Okay, yeah, so got it. So N and d omega, that's this cos theta, right? That's the projection of the direction of my photons over the projection of my photon in the direction n. Yeah, so that's where I get this cos theta from. And this 1/4 pi here is like, it's actually just defined in a kind of per solid angle, definitionally. So why does it look funny to you? It's because even though you know about Stefan Boltzmann, you wouldn't necessarily know about the very, very specific way it was defined in the first place. Yeah. Why am I averaging over a solid angle? Why am I doing, it's because that's how it was defined. Yeah. The amount, the solid, yeah. So it's the flux, it's the amount of light going direction and averaged over the solid angle, blah, 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 blah. Okay. So that's all the stuff that we need to take into account in order to get just the numerics right. Change things a little bit. All you're going to do is, instead of getting like a pi squared over 60, you'll get like a pi squared over 14 or whatever it is, right? So it just changes the prefix a little bit. But if you want to get all of the numbers right, you need to do all of those like dot products correctly and so on. Okay. Don't worry about it too much. Yeah. But it's just to show that you can get there and like, yeah. Any more questions? It's a good place to stop. Tomorrow morning, 9 a.m., we're going to do solids at your request. I love doing the solids because we get two different ways of looking at the heat capacity of solids. One of them is the method called Debye model. And they've asked me to teach the Debye model, despite the fact that it's manifestly stupid. And then the Einstein model. Oh, it's the other way around. Einstein model first, which is manifestly stupid. And then the Debye model, which is not. Yeah, sorry, I had it the wrong way around. Yeah, I always forget which one it is. Yeah. Yeah, Einstein, big idiot, did it wrong. Debye, real smart, did it right. Okay,